talk about simplifying expressions involving exponents. And the first thing that you have to recall in order to do this is that there are a bunch of rules or laws that sort of tell you how expressions involving exponents can be simplified. So here are the first handful of them. First of all, x to the 0 is equal to 1. All that really means is that anything to the 0th power is automatically 1. Next we have x to the a times x to the b is equal to x to the a plus b. So what this is saying is that if you multiply two expressions with the same base, then you add the exponents. Then we have x to the a over x to the b. That gives you x to the a minus b. So what this is really telling you is that if you have one expression involving an exponent divided by another, then you will subtract the exponents. Then we have the following rule. We have x to the a to the power of b is equal to x to the a times b. So what this really tells you is that when you have something raised to a power and then raised to another power, then you multiply the two exponents. Then we have xy to the a is equal to x to the a y to the a. This essentially says that exponents distribute over multiplication. This is multiplication happening between the x and the y, and the a is sort of being distributed to each of those two terms here. Note that although this is true, although exponents do distribute over multiplication, they do not distribute over addition. So for instance, it is not true that x plus y to the a is equal to x to the a plus y to the a. That is not true. Okay, it's a very common mistake, so be aware of it. Some other rules are that x over y to the a is equal to x to the a over y to the a. So all that really says is that if you have a fraction raised to a power, then you can distribute that power to the top and the bottom of the fraction. That's all it's really saying. Then we have the following. This is the rule for negative exponents. X to the negative a is equal to 1 over x to the positive a. This rule is, it looks simple, but the behavior that it describes is sort of complicated. I suppose that one way of describing this is the following. If you have an object raised to a negative exponent, then what that means is you put that object, the x in this case, in the denominator of a fraction, and you make the exponent positive. But as we'll see, this rule doesn't really fully describe the behavior of negative exponents, I don't think. I think it's a bit more complicated than this rule is letting on. And then finally we have fractional exponents. So x raised to the power of m over n is equal to the nth root of x to the m. So, the key thing to take away from this is that basically if you have a fractional exponent, then really that is referring to some kind of root. In this case, as you can see, the denominator of the fraction gives you the order of the root. So if n is the denominator, then n is the order of the root. So if that's a 2, then you're looking at a square root. If that's a 3, you're looking at a third root, and so on. A quick comment, this expression here, the nth root of x to the m, can actually be written slightly differently. Another way of writing this expression is the following. You can write the nth root of x quantity to the m. You might be wondering, what's the difference? Well, here what you're doing is first you're taking x and raising it to the mth power, and then you're taking the root. Here you're taking the root first and then raising to the mth power. It's important to note that these two expressions are equal. In other words, it doesn't matter whether you raise to the mth power first or whether you take the root first. Oftentimes, this expression is easier to evaluate than this one, so it's good to know that you can represent it in both ways. That's kind of it, although there are a couple of additional rules which are really helpful to know. So one of them is the following. It's x to the negative 1 is equal to 1 over x. That is really just a specific example of the more general rule, x to the negative a is equal to 1 over x to the positive a. So this is just this rule here, except with the specific value a equals 1. But this comes up often enough that it deserves to be mentioned explicitly. A couple of others that are useful. If you have a fraction x over y to the negative a, that is the same thing as y over x to the positive a. You can actually prove this rule through the rules that I've already written down. So I'm not really giving you anything new here, but this is a useful shortcut. If you see a fraction raised to a negative exponent, then you can in fact flip the fraction upside down and then make the exponent positive. It's a good one to know. As a specific example of that, if a is equal to 1, if you have x over y to the negative 1, that's really just y over x to the positive 1. Here I'm using the rule that I just wrote down here with a equal to 1. But of course, y over x to the positive 1 is really just y over x, because anything to the 1 is itself. So the fact that raising a fraction to the negative 1 simply flips the fraction upside down is useful to know. All right, so now that we've established all of the basic rules for manipulating expressions involving exponents, let's look at some examples. Let's simplify. So here's our first example. Let's simplify the following expression. B squared over a to the negative 2 times a squared over b to the negative 3. This is kind of a nightmare, but we're going to make it as simple as we can. All right, so let's begin by looking at this fraction. First of all, this negative exponent is kind of annoying. Negative exponents kind of suck in general. So we can actually use the rule that I wrote up here a moment ago, which says that, if you've got a fraction raised to a negative exponent, you can just flip the fraction upside down and make the exponent positive. So let's do that. So let's just take this fraction, flip it upside down. So that gives me a over b squared, and now I can make the exponent positive. So that's going to be positive 2. And I can do the same thing over here, right? I can just flip this fraction upside down because I've got a negative exponent here, right? So I can flip this thing upside down. That gives me b over a squared raised to the positive 3, right? At least now we have no negative exponents, which is an improvement. Negative exponents suck. All right, so now what we have to do is sort of distribute, this 2. If you remember, we have a rule which says that, in general, if you have x over y to the a, if you raise a fraction to a power, then all you really do is raise the top and the bottom to that power. And so that's the rule that I'm going to apply here. I'm going to raise both the numerator and denominator of this fraction to the second power. So what do I get? Well, if you raise a to the second power, of course you're going to get a squared. And if you raise this object to the second power, what are you going to get? Well, if you take b squared and square it, you're going to have to apply the so-called power of a power rule. If you remember, that says like x to the a raised to the b is equal to x to the a times b. So, when you take an object and you raise it to one power and then raise it to another power, you multiply the exponents. And that's exactly what's happening here. The b squared is going to itself get squared, so that's b squared squared. So it's a power of a power, so you multiply the two exponents. That gives you b to the 4th. Over here, it's a very similar kind of situation. We just have to raise both the top and the bottom to the 3rd power. That's going to give us b to the 3rd over, and then here, once again, we have to think of this as a power of a power. a is already being squared, and if you raise that to the third power, you have a to the second to the third, and you're going to use this rule and multiply the two exponents. So that's going to give you a to the sixth. Now there's basically cancellation. Technically, there's a few different ways of thinking of this. You could think of this as like a squared over a to the sixth, and then use that rule about subtracting exponents. Like you could think of this as a squared over a to the sixth, which is a to the 2 minus 6. But what I recommend is really just to look at this expression and say to yourself, yeah, I've got a's on top and I've got a's on bottom. I know that a bunch of them are going to cancel, and really, I know that after cancellation, I've got 2 copies of a on top and 6 copies on bottom. I know that after cancellation, there are only going to be 4 copies of a left over. The only question really is, where are those leftover copies going to be? And the answer is on the bottom. The reason the leftover copies of a are going to be on the bottom after cancellation is that there were more copies of a on the bottom to begin with. Okay, so after cancellation, there are going to be 4 copies of a on the bottom, so we have a to the 4th on the bottom. A similar thing occurs with the b's. You got 3 copies of b on the top, you got 4 copies of b on the bottom. You know that after cancellation, you're only going to have 1 copy of b left over. The only question is, where is that leftover copy of b? Is it going to be on top or on the bottom? The answer is on the bottom, because once again, there were more copies of b on the bottom to begin with. So I'll just place that b to the 1 on the bottom. Obviously, b to the 1 is the same thing as just plain old b, but whatever. Now, if you notice there's nothing left in the numerator, in that situation, you have to write a 1, as you probably remember. And that's simplified. I guess maybe b to the 1 should just be b, but whatever, good enough. Okay, let's do a different kind of example. So here's our second example, example 2. Let's simplify the following expression. A to the negative 2 plus b to the negative 2 raised to the negative 1. Now, it's really tempting to think that you can distribute this negative 1 to each of these 2 terms, but if you remember what I said a few minutes ago, exponents don't distribute over sums, only over products. So unfortunately, you can't do that. What you have to do, unfortunately, is use the rules for negative exponents again and again. Let's start by looking at the inside, okay? I'm not going to mess with this exponent right away. Notice that a to the negative 2, we can use the rule for negative exponents to write that as 1 over a to the positive 2, right? That's what a negative exponent means. It's 1 over, and then you make the exponent positive. Similarly, this b to the negative 2 is really just a 1 over b to the positive 2, okay? Now, okay, we've taken care of the negative exponents here, but how do I take care of this one here? It's a little difficult to wrap your head around, I suppose, but what we have to do is we have to take this entire object and write 1 over that entire object, right? Because that's what this thing tells you to do. Raising this object, raising any object, to the negative first power means take 1 over that object. So this whole object is being raised to the negative first, which means that I have to write 1 over this entire object to the positive first power. Of course, the positive 1 is not really doing anything, so we can kind of just leave it as 1 over a squared plus 1 over b squared. All right, now this expression no longer involves negative exponents, which is good. However, it's what is called a complex fraction. We've got fractions within fractions, and that's bad news. We have to convert this into a simple fraction. That is a single fraction with 1 numerator and 1 denominator. to do that, what you have to do is obtain a single fraction up top and obtain a single fraction down below. This object here, I suppose, isn't technically a fraction, but you can think of it as 1 over 1. However, the object in the bottom is definitely not a single fraction. We need to make it a single fraction. So let's do that. And how do we do that? Well, you know, we have to add these two fractions together, which means we need common denominators. So in order to obtain common denominators, I'm going to multiply top and bottom here by this denominator, b squared, and I'm going to multiply top and bottom here by that denominator, a squared. So multiplying top and bottom here by b squared, I get b squared over a squared b squared plus, and then multiply top and bottom of this fraction by a squared. So I have a squared over a squared b squared. These two fractions now have common denominators, which means that I can combine them, so I will do so, and I get b squared plus a squared over a squared b squared. Now that the denominator of this larger fraction is a single fraction, we can use what I like to call keep it, change it, flip it. If you haven't heard this before, keep it, change it, flip it. It really just means multiply by the reciprocal, but it's kind of a cute way of saying it. So what does keep it, change it, flip it mean? It means you keep the numerator the same. So that's just 1. Change it means you change this division bar to multiplication, and then you flip it. Well, flip what? Well, flip the bottom fraction. So that's a squared b squared over b squared plus a squared. So that's keep it, change it, flip it, or if you like, dividing by a fraction is the same thing as multiplying by its reciprocal. Okay. So anyway, if you look at what we have 1 times this big expression here. The 1, of course, isn't doing anything, so we can just write a squared b squared over b squared plus a squared. That is simplified. Okay. All right. So let's maybe do one more example before we move on to solving equations. Let's have a look at the following. So here's example 3. Let's look at the following expression. Let's try to simplify x to the 5th plus x to the negative 2nd over x to the negative 3. This is kind of tricky. So here's what I would say. I would say that when you have negative exponents inside of a fraction, you could, of course, write the following. You could say, oh, this is x to the 5th plus, and then x to the negative 2 is 1 over x squared, and then x to the negative 3 is 1 over x to the 3rd. That's a perfectly good way of thinking about it, and I think actually that's how I'm going to think of it here. So just using the definition of negative exponents, this is what I get. Now, this looks kind of like a mess, but if you look carefully, what's happening is you're dividing, you're taking this whole expression here in the numerator of the large fraction, and you're dividing by this fraction here. And, you know, if you're dividing by a fraction, you know what that means. Dividing by a fraction means multiplying by the reciprocal, or if you like, keep it, change it, flip it. So this is going to be, so I keep the numerator the same, x to the 5th plus 1 over x squared. I change the division to multiplication, and then I flip that upside down, so that's x to the 3rd over 1. Now, as I've written it right now, there's actually a mistake, and the reason I've made this mistake is basically that it's a really common student mistake. The problem is that this entire numerator was supposed to get multiplied by the reciprocal of this fraction. But I have not multiplied this entire numerator by the reciprocal of this fraction. If you look at this expression here, if you look at it carefully, I'm only multiplying this second term by the reciprocal of this fraction, when actually I want to multiply the entire numerator. So one way I can do that is put this thing in parentheses. Right? Now the entire numerator is being multiplied by the reciprocal of that fraction. Now it's pretty simple. I just have to distribute this thing, you know. So what do I get? X to the third over 1 is obviously just x to the third. So x to the third times x to the fifth, we add the exponent, so that's x to the eighth plus. And then when you multiply this thing against this thing, you have x to the third over x squared, right? But of course, x to the third over x squared, you can cancel two of the x's and be left with x to the 1, or just plain old x. So that's that is simplified. Okay. Okay, so now we're going to move on to the second portion of today's lesson, which is about solving exponential equations. So I guess I should start by saying, what is an exponential equation? An exponential equation is just an equation where the variable is inside of the exponent. Like, for example, 9 to the 4x is equal to 81. So as you can see, this is an equation where the variable is inside of an exponent. So therefore, it's an exponential equation. Today we're only going to learn how to solve a particular type of exponential equation. I'll explain exactly what that type is in a moment. But for right now, I just want to point out a key fact. So here's the key fact that we are going to rely on today to solve exponential equations. It's the following. A to the x is equal to a to the y if and only if x is equal to y. So, let's just look at this equation for a moment. What is it really saying? It's saying that, if you have two exponential expressions equal to one another, where the base, a in this case, where the base is the same, it follows that the two exponents must be equal as well. So we'll see how this fact can be used to solve an exponential equation. So let's actually return to this equation right here, the exponential equation that I began with. Let's solve that exponential equation using this key fact. So how can we do it? The big idea, okay, with solving this exponential equation, and the big idea throughout the rest of this lesson is the following. We need to rewrite both sides of the equation as powers of a common base. Okay, the idea basically is you want to get the equation into this form, where both the left and the right-hand side are simply something to a power. Right now, that's not the case. On the left-hand side, we have 9 to the 4x. On the right-hand side, we actually don't even have an exponent. But I claim it is possible to rewrite both sides of this equation as a power of a common base. What you should notice about these two numbers, 9 and 81, is that they are both powers of 3. And that observation is the crucial observation for solving this equation. So knowing that both 9 and 81 are powers of 3, we can actually rewrite both sides of this equation as a power of 3. And that's exactly what I'm going to do. So 9, of course, is 3 squared. So I'm just going to replace the 9 here with a 3 squared. So I have 3 squared, and that 3 squared is being raised to a 4x. So I have 3 squared to the 4x. 81 is also a power of 3. What power is it? I think it's actually 4, right? 3, 9, 27, and 81. Yeah, so 81 is 3 to the 4th. Okay. If you notice, we're getting a little closer to that form. It's almost, a number to one thing equals that same number to the other. Almost. But the left-hand side has to be simplified. If you notice, we've got a power of a power. We have 3 squared raised to the 4x. What do we do when we have a power of a power? We multiply the exponents, right? So that's what I'm going to do here. So I'm going to multiply the 2 and the 4x to get 8x. So I have 3 to the power of 8x equals 3 to the 4. This equation here is now in exactly this form. It is, a number raised to something equals that same number raised to something else. It's 3 to the something equals 3 to the something else. And this key fact tells us that the only way that this can happen is if the two exponents are actually equal to each other. So I am now allowed to equate the two exponents. So I can actually write, this implies that 8x has to be equal to 4. Which of course, this is no longer an exponential equation, it's just a regular linear equation, and I can solve it by dividing by 8. So I get x is equal to 4 over 8, which is 1/2, and that's the solution. So, why did this work? And what was the strategy that we really used here? What we did was we started with our initial equation here, and we made the observation, both sides of the equation, the 9 and the 81, those can both be written as powers of the same thing, 3. And we used that fact, to rewrite the equation in the form 3 raised to one thing equals 3 raised to something else. And this key fact says that whenever that happens, you are allowed to simply equate the exponents. And that's why this works. Now, a word of caution, this is usually not possible. This process usually doesn't work. It's usually not possible to get both sides of the equation in this form. All the equations that we solve today will be solvable by that method, but later on in the unit, we will see lots of equations for which this strategy doesn't work, and you have to use something called logarithms. But for right now, let's just try another example. Let's do a much more complicated example. Let's do kind of a brutal one, I guess. So let's take a look at, so here's our next example. I'm going to write the third root of 8 to the power of x plus 1 over 16 to the power of x is equal to 32. This equation obviously has variables in exponents. You've got an x and an exponent here. You've got the x plus 1 and the exponent of the 8 right here. So yeah, it's an exponential equation. I claim that this can be solved using exactly the same strategy we just used. What you have to notice is that the numbers here, 8, 16, 32, they are all powers of the same thing. They're all powers of what? They're all powers of 2. 8, 16, and 32 are all powers of 2, and it is that observation which will allow us to rewrite the equation in a helpful form. So let's go ahead and rewrite each of these as powers of 2. So I have third root of, well, what is 8? 8 is 2 to the third, isn't it? So I'm going to replace the 8 with 2 to the third. So I have 2 to the third to the power of x plus 1, over, I'm going to replace this 16, well, what is 16? It's 2 to the 4th, isn't it? 2, 4, 8, 16? Yeah. So that's 2 to the 4th raised to the x, right? And then over here, 32, I'm going to replace that with 2 to the, I believe it's 2 to the 5th, isn't it? 2, 4, 8, 16, 32, yeah. Okay, now we've rewritten those numbers as powers of 2, that's great, but basically we have to simplify this left-hand side of the equation a lot before we can use the machinery that we used in the previous problem before we can equate exponents. So there's a lot to do here. Maybe I'll just start by noticing that we have powers of powers here, 2 to the third to the x plus 1, right? And 2 to the fourth to the x. So what do we do when we have powers of powers? We multiply, right? So I'm going to multiply these two exponents, right? 3 times x plus 1. And be careful, the 3 is going to multiply the entire x plus 1. In other words, the 3 is going to multiply both the x and the 1. So we're going to have 2 to the power of 3x plus 3. Okay? In the denominator, you're multiplying the 4 and the x. That, of course, gives us 2 to the 4x. And the right-hand side, I'm not going to do anything. It's still just 2 to the 5th. All right. So now what? Actually, I think I'm going to turn on the light here. It seems a little dark. All right. So now what we have is we have 2 to the something divided by 2 to the something else. Remember the rule that says if you have something like x to the a over x to the b, that's really equal to x to the a minus b. That's the kind of situation that we have here. 2 to the one thing divided by 2 to the something else. We're going to subtract the exponents. So I have third root of 2 to the power of this exponent minus this one. So that's 3x plus 3 minus 4x. That's going to give you negative x plus 3, right? 3x take away 4x, that's negative x. All right, and again, I'm not doing anything to the right-hand side. Okay, we have to address this third root. Remember that roots really are exponents in disguise. They're simply fractional exponents. What does it mean to take the third root of this object? It means to raise this object to the 1/3 power. So I'm going to rewrite this left-hand side. That's 2 to the negative x plus 3 raised to the 1/3 equals 2 to the 5th. So now, finally, I have a power of a power once again, so I just have to multiply these two exponents. But be careful, again, make sure that this exponent multiplies all of the terms in this one. The 1/3 is going to distribute to each of these terms. So that gives me 2 to the negative 1/3 x plus 1/3 times 3 is going to give me 1 equals 2 to the 5th. So now this equation is finally in the form that I had in the previous example, namely we have the same base with different exponents. And that key fact from the previous page allows us to conclude that this implies that the two exponents have to be equal. So I can conclude that negative 1/3 x plus 1 is equal to 5. And now it's no longer an exponential equation, but rather just a linear one, so it's easy to solve. I'll just subtract 1 and then multiply by negative 3. I get x equals negative 12, and that is my solution.